The topic for this lesson is Lagrange multiplier. So we have two objectives, two goals. By the end of this lesson, you'll be able to find maximum and minimum values using Lagrange multiplier, and you'll be able to solve applied problems involving Lagrange multipliers. Okay. Now, first of all, what is Lagrange multiplier? So recall that in the previous section, we did optimization, right? But in that case, all the functions came by itself. We did not place any restrictions upon the values that the independent variable can assume. Okay, those kind of problems are sometimes called free maxima and minima, or free optima problem. There is no condition imposed. There is no constant imposed. But you see, in the real world situation, oftentimes restrictions or conditions are placed upon the values of independent variable. Okay, so these problems are referred to as constant optima or constant optimization. And there is an approach, there is a method to solve those kind of problems that includes the constant or condition. And in that case, what we do is we impose one additional variable and we call it Lagrange multiplier, and we denote that by lambda. Okay, we add one extra variable. Whatever variable is given in the question, given in the function, we imposed one more variable, lambda, called the Lagrange multiplier. And there are basically two methods for Lagrange multiplier. And one method is that, first of all, suppose we're given a function f(xy). It's an objective function, I call it. Okay, we have objective function, a function that we want to maximize or minimize. But that function comes with some constant, another function, and we call it constant function. And in that case, you see we have a function. It's an objective function. This is the function that we want to maximize or minimize. And we have constraint function. And let's say this denoted by this one. Then the Lagrange multiplier tells us that nebula f(xy), it's a vector, it's a gradient vector, we call it nebula, and then we read this by nebula. Okay, nebula f(xy), which is sometimes called a gradient vector of f, equals lambda. This is lambda z and gradient vector of gxy. Okay, or nebula gxy. That's one equation. And then another equation is simply whatever is there, gf equal to 0. This is the method given in your book. But now the issue is that we have not done the gradient vector. You don't know what is gradient vector yet. And we'll not do this in this course. Basically, those gradient vector concept, we cover this concept in Calculus 3 for science and engineering people. So since we have not covered this, I'm gonna follow a different method, okay, which is not given in your textbook, but that will make your life easy, guys. Okay, you don't need to know the what is gradient vector. What is that nebula f(xy) represent? Basically, what this represent is, let me write this quickly. It is a vector And this represents the partial derivative of f with respect to x, partial derivative of f with respect to y equals lambda. This one partial derivative of g with respect to x, partial derivative of g with respect to y. And so you can actually put them separately. The component wise, f of x equals lambda g sub x, and f of y equals lambda g sub y, and then g of xy equal to 0. So we have equation 1, equation 2, and equation 3. We solve these three equations. That's one method. And maybe we will try by using this method just for fun, but I'm going to introduce a different method here, okay? Let's look at example 1. Find the maximum value of, okay, we are given a function. Let me represent that by f. Find the maximum value of f of xy equals xy subject to the constant x plus y equals to 20. So here what is given is we want to maximize this f function. Okay, our objective function is f xy equal xy, and then the constant function is, or condition constant function is x plus y equals to 20. Now, one thing, here is the step that we're going to follow. Always make sure that the constant function is 0 on the right hand side. Make sure that the constant function always has 0. So constant function, I will write this x plus y minus 20 equal to 0. Make sure that the right hand side is always 0. Okay, so I'll write this as xy equals x plus y minus 20 equal to 0. I represent this function by this function here by g functions. Okay, this is the constant function. All right, now step 1. In step 1, form an auxiliary function capital F xy lambda, which is given by f of xy minus lambda g of xy. So step 1 is form f xy lambda. We introduce a new variable lambda equals, which is given by the objective functions minus lambda times constant function always. Okay, and this function is called, Lagrangian function. Okay, Lagrangian function. So step 1, you create a Lagrangian function. How to create that? Always the objective functions minus lambda times constant function. Always do that, okay? Objective functions minus lambda times, and lambda is a constant. It is called, this lambda is constant, and this is called Lagrange multiplier. Lagrange multiplier. It is a constant. Okay, so that means our function f xy lambda equals xy, because our f function is simply xy minus lambda times x plus y minus 20. Okay, because zxy is x plus y minus 20. I just copy that down. Step 1 is done. Any questions so far? Step 2. So in step 2, our goal is to find the critical points. Okay, to find the critical points, find the first partial derivative and solve the system, which is the first derivative equal to 0 gives us the critical number. So the second step is to find the critical number, to find critical points. All you need to do is find the capital F. Remember, I'm talking about the capital F here, X. Calculate that, which is Y minus lambda. Does that make sense? Because see here, this guy right here, if you simplify, you're going to get xy minus lambda x minus lambda y plus 20 lambda. So that's what you're going to get. And then derivative of this function with respect to x will be y minus lambda. Okay. And your partial with respect to y is going to be x minus lambda, and then partial with respect to lambda is going to be partial of f with respect to lambda is going to be how much? This will be negative x plus y plus, minus 20. All right, so we found the first partial derivative of Lagrangian function, capital F sub x, capital F sub y, capital sub F sub lambda. So now, for critical point, maybe I'll write this way. So step 2, find okay, I'll write step 2, find this one, and for critical number, critical points equal to 0, first order derivative 0, first order derivative with respect to y is 0, first order derivative with respect to lambda is also 0. So we got one equation here, which is y minus lambda equal to 0. This one is x minus lambda equal to 0. This one is x plus y minus 20 equal to 0. So from this one, you will get y equals to lambda. From this one, you will get x equals to lambda. And if you combine them together, you're going to get x equals to y. Does that make sense? Now, you substitute. All we need to do is we need to solve this 3 equations. So this is, let's say, equation 1. Equation 1. This is your equation 2, and this is your equation 3. So you can solve this 3 equations the way you want. I think the easiest one would be from here we get y equals to lambda, x equals to lambda. So it tells us that x and y are equal. I'm going to substitute this value there. So I'll get x plus x minus 20 equal to 0. And simplifying, you're going to get x equals to 10. So if x equals to 10, because x and y are equal, so x equals to 10 equals to y. Because you see, we know that x and y are equal. Okay, so the critical point is 10, 10. X is 10, y is 10. Let me go all the way here now. So critical point is 10 and 10, xy, 10 and 10. Okay, then what is the maximum value? So maximum value occurs at 10, 10, and maximum value is f of xy equals xy. That means f of 10, 10 equals 10 times 10, which is 100. Okay, that is your maximum value. Now, remember, we have not done any test, second derivative test. We know that the critical point is the candidate for maxima and minima. But in this case, what we did is we say that this is maximum. And that's what we're going to do. The mathematical proof that this is maximum is not required as long as you follow the Lagrange multiplier in this course, in all the questions. And if the function tells you to find the maximum value, and you will end up with maximum value. If it says minimum value, it will end up minimum value in general. Again, we can prove it that this is maximum, but the proof is not required. That's out of the scope of this course. What we do instead is that some of you may raise the question, so well, how do you know that? Let us verify that this is the real maximum by experimental method, okay? Let us do some observation. If we have any doubt, let us do observation. So notice that our function is xy, and the condition or constant is x plus y equals 20. That is the condition. What I'm claiming is I'm claiming that when x is 10 and y is 10, then our function value is 10 times 10, because x times y, which is 100. And I'm claiming that this is the maximum. Let us try a couple of other possibilities. So if I suppose x equals to 9, then what is your y? See here, when x is 9, y, x plus y is 20. So that means y must be 11, right? So it is 11. In that case, you'll get 9 times 11, which is 99, less than that. Let us try x is 8 and y is 12, for example. What happens? 8 times 12, which is 96, even less than 100. In the same way, if I continue, let's say x is 1 and y is 19, for example. Then this will be 1 times 19. That is simply 19, right? So from all the possible combination, we have seen that this one is actually the maximum, okay? So I think you are convinced yourself that this actually is the maximum, but again, the mathematical proof is not required in this case. Any question? Okay, so now let us work with example 2 just for fun. It's the same process. In this case, using the method of Lagrange multiplier, find the relative minimum of the function. Okay, we want to minimize this function. All right, so the goal is to objective function equals 2x squared plus y squared. And the constant function is x plus y equals 1. So remember, constant function, what we do is we always get the right hand side equal to 0. And so we denote that constant function by g of xy. So we have two functions. One is f, one is g. f is the objective function and g is the constant function. All right. Now, step 1, create Lagrangian multiplier. I simply write f of x, capital F. So f of x, y, and lambda equals minus lambda g of x, y. So we get f x, y, lambda equals 2x squared plus y squared minus lambda x plus y minus 1. Now, step 2, find f capital F x of x, partial derivative of capital F with respect to x, partial derivative of capital F with respect to y, and partial derivative with respect to lambda. Find this one and critical number. So that's all we need to do in step 2, critical points. Okay, guys, you have 3 variable and 3 equation. You can solve it. I trust that everybody is able to solve it. I just write solving equation 1, 2, and 3. We get x equals what? Y equals what? Let me know. What do you get? Type your answer in the chat box, okay? In the chat box in Zoom. Okay. So many people got here. Many of you got x is 1/3 and y is 2/3. I trust that this is the right answer. Okay. Therefore, critical point is, so I'll write here. So critical point is 1/3 and 2/3. All right. Now, the question is, find the relative minimum. Okay, let us find the minimum value. So what it means is, so the function f of xy equals 2x squared plus y squared has minimum at 1/3 and 2/3. And the minimum value is, let us calculate the minimum value. And minimum value equals f of x is 1/3 and y is 2/3 equals 2 times 1/3 square plus 2/3 square. And how much is that? Let me know. Calculate this and let me know. My calculator tells me this is 2/3, but I want to verify this answer with you guys. Okay, so many of you got 2/3, so I think that must be the correct answer. And that's it. Done. So far, we have looked at only the pure mathematical questions. Now, let us look at one application questions here. Okay, how can we apply this Lagrange multiplier concept to solve real world problems? Let's look at example 3. All right, example 3. Because of terrain difficulties, 2 adjacent sides of a fence can be built for $6 per foot, while the other 2 adjacent sides cost $4 per foot. Adjacent side means suppose this cost $4 means this also cost $4. Okay, if this cost $6 means this cost $6. Or the other way around. Okay, doesn't matter. All right, that is given. Now find the field of maximum area that can be enclosed for a total budget. You see the condition is given here. The constant, like I said earlier, in the real life situation, then pretty much every every function comes with constant, with condition. So your budget is just $1,200. You don't want to invest or spend lot of money in that project. The project has $1,200 only, and that kind of situation always comes in the real world problems, right? So let us try this. First of all, let x equals x represent the length, and y is width of the field. Now, I suppose that this is our x and this is our y. X feet, all right. It is x feet. And this one width is y feet. Okay, x feet and y feet are the length and width of the field. Now, our objective function is objective function. What is our goal? What is our objective? Objective function is find the field of maximum area. Remember, our goal is to maximize the area. That is the objective function. That is the goal. Objective function is fxy is, what is the area of the rectangle? Area of rectangle. So area of rectangle is basically, we know that that is x and y. So that is our objective function. Now, what is the constant function then? So the constant function is total cost is $1,200. Let us find the cost here. So for this side, okay, it costs $4 for 1 foot, and the length is x feet. Therefore, the total cost here, cost for this side is 4x. Cost for this side is 6y. In the same way, you can calculate the other side. So the constant function is total cost is less than or equal to $1,200. That is the condition. So total cost means 4x plus 6y plus 6x plus 4y. Okay, this is x, sorry. This is x and this is y. So this 4x plus 6y plus 6x plus 4y. So that is the total cost, which is less than or equal to $1,200. Okay. But to make life easy, what we're going to do is we'll simply write the equal sign. Okay. So in this case, you got 10x plus 10y equals 1,200. So that gives me x plus y equals 120. Okay. So you can write this as x plus y minus 120 equal to 0. And we represent this by gxy. Okay, we have the objective function, we have the constant. Now you know how to do it. So we want to maximize this subject to the constant x plus y minus 120 equals 0. Okay, so we have the function, we have this one. So now create step 1, create the Lagrangian function. So step 1, create Lagrangian function, which is given by f of xy lambda equals f xy minus lambda gxy. So which gives me xy minus lambda x plus y minus 120. Okay, so now step 2, you find, I'll write a step to the other side. I don't have a space here. Here to here. Step 2. So find first order partial derivative with respect to x, y, and lambda and critical numbers. Critical point. Okay, let us calculate this. So partial of capital F with respect to x is y minus lambda with respect to y. I trust that you guys can do it by yourself. Okay, try working on your own. If you need help, look at there. Otherwise, just try yourself. Okay, solve these three equations. So here from this one, you'll get y equals lambda. And from this one, you'll get x equals lambda. That is very similar to, I think, example 1 that we discussed. So if you combine these two, so from here, we'll get x equals y and substitute the value there. And you're going to get x plus x minus 120 equal to 0. So you'll get x equals 60 solving this. So since x and y are equal, hence y equals x equals 60. So the critical point is therefore f of xy equals xy is maximum at 60, and maximum value is going to be f of 60 and 60, which is 60 times 60, and that's going to give you $3,600. I mean, oh, what is the unit? Feet or meter? It's feet. So because it's an area, so it will be feet square. So with that $1,200, you can enclose 3,600 feet square area, 3,600 square feet. Any question, guys? Okay, if you don't have any question, maybe this example 4, I leave it to you. Just try this on your own. Very similar idea. And if you have any difficulty, then we will we'll try in class in our next class. Okay, we'll try this in our next class, but I suggest I would like you to do it by yourself first. So this is all about Lagrange multiplier.